Okay? Okay, let's get started. Hello, ladies and gentlemen. My name is Nicolas Février, and I will be your host for the next 90 minutes. And we'll talk about a session named SP Security, Leveraging BGP Flowspec to Protect Your Infrastructure. That's a very long term to what could have just been a BGP Flowspec deep dive. It's part of service provider track, and we will see that it's not only applicable for service providers, it's also about security, but not only. We'll talk about Flowspec more globally. We will see that it has been introduced mostly with SP security in mind, but now we have customers using it for very different purposes. Traffic steering, traffic engineering, that's what we're gonna cover today. So it's a deep dive on BGP Flowspec. If you want to reach me, that's the easiest way, Twitter. This Twitter handle is one good way to reach me, but also, as usual, you know, that's your third day at CiscoLive, so you know, if you have specific questions, don't hesitate to go to the Spark room and engage a discussion. What we want to do during this 90 minutes is the following. We want to introduce Flowspec. We want to explain what it can do, also what it cannot do, and where it can be a good fit for your network. Flowspec is nothing else than just a tool. So we're going to describe what it can do, and that's really the purpose of this discussion. We'll cover DDoS, because that was the initial target of this tool, but we will go further than that, and we'll talk about many other things. Who am I? So my name is Nicolas, as I just said. I'm based in Paris. I'm a technical marketing in the service provider business unit. And I've been working for 14 years now in Cisco. So what I've been doing in Cisco is mostly iOS XR platforms. So I've been working since the very beginning on CRS1 and on every single hardware router up to the very latest, the NCS 5500, which is my main product today. What I also did is the following. Yesterday, I took a quick look at the list of attendees, and I tried to identify who are you. So yesterday evening, we had 62 people registered to this session, and half of them were part of the let's say, the service provider hosting world. So it was really something interesting. I don't know how many of you, if I can have a quick show of hands, are part of the service provider, or let's do the opposite, who are not part of service provider. That's, oh, okay, that's not too bad. That's, actually, I count, let's say, 10 people, more or less, that are not. That's very interesting. It's a big trend. The same session 2 years ago was 90% service provider only. Now we see that we have more and more interest in other categories. Also, what we see as non-service provider are big enterprise, government, education, also a lot of consulting companies interested in the technology. So, the program for today is the following. We do have, we will go through a protocol description, so it's interesting to see what the protocol is made of in terms of RFCs, draft, and so on. What is our implementation? And we will see how to configure it. Very important will be the last section, how we want, all the limitations we want to avoid. So that's the caveats and limitations. That's, for me, the most important point to understand when you're going to deploy the technology, what can be done and not done. So a few words of thanks for these guys who have been very helpful for this session. Some of them have been part of the standard process. They have been working at IETF. Some others have helped us with demos and so on. So thanks to these people. They are very helpful for this session. We have quite a large not PowerPoint, PDF on this. You will see maybe 170 or 80 slides. Don't worry, there is no time to go through that number of slides in 1 hour and a half. So there is a lot of them in the backup section, particularly the troubleshooting. All the more advanced configuration tricks will be in the backup section. So it will be very useful in the future if you start deploying and you need to go a bit deeper in the understanding of the protocol, if you want to understand how are encoded the NLRI and so on. That's really what you will see on this backup section. Also, we will have slides where that are flagged for reference. So in these slides, we just want to touch just one point or two, but we will not go through all the list of items described. We will it's going to be for your consumption later on if you are interested. Let's directly jump into the deep dive and talk about the protocol. BGP Flowspec has been introduced and ratified at IETF in 2009. That's already 9 years ago. So it's not a new technology in any way. It has been, the working group started almost 2 years before that, so let's say it's something that is already 11 years old. Not a new technology, absolutely. The main idea here was to separate the control plane and the data plane. But it was way before we talked about SDN. The idea is to indicate, to signal remotely what should be programmed and how the packet should be handled when they are received on the router. So we will have a controller, we will have a client, and the client will receive instruction of what it should do, how it should manipulate the packets based on what a central point decided. Initially, I mentioned before, it was made for DDoS tackling, DDoS mitigation. Nowadays, it goes way, way beyond that. A lot of customers are using it for redirecting the traffic the way they want. We will see a couple of use cases to explain this. So, important word, what BGP Flowspec is not, and that's an important clarification point here. I often meet customers that are telling me that Flowspec is NetFlow, and they are absolutely unrelated technologies. NetFlow is a monitoring technology, something that will sample traffic going through your routers or your devices to extract information that will help you build matrix of flows, matrix of traffic. Flowspec has no visibility of what's going on the network. It's just a way to signal action remotely. So there are two technologies you're going to use together, NetFlow for monitoring what's going inside your network, Flowspec to influence what's going, the packets going through your boxes. So absolutely no relation between the two. Also, I've seen many times confusion with OpenFlow. That's an interesting one. It was the very first protocol at the beginning of the SDN story. In many ways, it's going in the same direction, and NetFlow will help you influence or remotely or take remote action, separating control plane and data plane, but they are not the same, of course. Microflow policing is also an interesting one. Microflow policing is UBRL, user-based rate limiting. It's a technology that is coming from the Catalyst years, available in the SR9K, that can influence traffic. You can rate limit traffic from one user for one particular port. But that's not something Flowspec can do. Again, different technology to different means. They all have in common the flow in the name, but that's it. Now it's clarified. Let's jump directly to the definition of Flowspec. We talked already about two key concepts, the controller and the client. The controller will signal remotely actions to your clients. It will explain to the client how it should handle the packets when they are received in ingress direction on an interface of your router. And for that, it will describe this traffic. We will use layer 3 and layer 4 information in the header, and it will signal an action. And that actions will be the following. Policy-based routing, how to redirect your traffic to a specific next stop address, IP, or to a specific VRF, to leak inside the VRF. Or it could be QS, how to remark your traffic with a specific DSCP field, or if you want to rate limit one specific flow, the value of the rate limiter, the policer. Finally, it will be also used for access list. In a sense, access list is nothing else than a rate limiter with 0 bit per second. So you can instruct remotely that you want to drop one specific stream or one specific flow. What we call a BGP Flowspec rule is the following. So first of all, rule is not route. People sometimes will say BGP Flowspec route. Okay, it's not exactly that. In the definition, we talk about rule. A rule is made of two parts. A description, where we're going to explain what should be the traffic of interest, and then an action, the one I described before, the policy-based routing, the access list, the remarking of the packet. A couple of examples I'm showing here. You have on the description what should be matched by your rule. So it's something that will match the destination address V6 on the first example, or your UDP 123, so NTP traffic, but with a specific packet size. Or you will have also capability to match TCP flags. I want to match every packet going to 1, 2, 3, 4 with a SYN flag positioned. Or I can match also the source with a specific port like HTTP. And my action will be the following here. I'm going to redirect into a specific VRF. So I'm doing VRF leaking. I will rate limit to 0, so I will drop all my packets like an access list. I will divert my traffic to a new next stop, which is not the natural next stop learned by IGP or BGP. Or I can remark my traffic. In this example, I'm using expedite forwarding. So matching action. And that's what we're going to signal to the clients. And this can be only done, again, with layer 3 and layer 4 information. We will describe that now in a second. So let's go over the two mandatory components of a BGP Flowspec architecture. First of all, you're going to need a controller, at least one. The controller needs to implement just a control plane. It does not need to influence the traffic, so you just need a control plane where you will be able to instruct the rules I described before, the description and the action. It needs to be a server, a router, or a virtual router. So by router, I mean everything running iOS XR can be a controller, or XRV, if it's a virtual controller, XRV 9000 can be used as a BGP Flowspec controller. Or it could be also a server or an application on a server, whether it's open source or commercial. Open source, I'm giving a couple of examples, ExaBGP, YaBGP, GoBGP, all open source solution you will find on GitHub if you want the source code. And also we have OpenDaylight modules for that. That's also open source. And we have commercial solutions, like the one with Arbor, ArborSP, or Radware. Other people are doing Flowspec controllers. So multiple options. This only implements the control plane again. They will instruct remotely through BGP the client. The client needs to implement both the control plane because they will receive this information through BGP, but they will need to derive this information and program it on the TCAM. So, or let's say on the hardware, on the forwarding ASIC. So they need both control plane and data plane. Controller can also be, a client can also be a controller. That's not, the two can be on the same box, but there are two different roles. And what could be a client is actually a layer 3 device, or a device like a router. iOS XC, like the ISR1K or the CSR1000V are potential clients, or all the iOS XR routers, CRS, ASR9K, NCS6K, but also soon NCS 5500 this summer. Finally, there is an optional element on the architecture. It's a route reflector. If you need to scale higher, you need to be able to have just one controller advertising a single session or generating a single session to a route reflector, which will be responsible for disseminating all the informations to all the clients. So that's a good way to not have to establish a session between your controller and every single customer. But you can still do that if you need to be very precise. So it's not mandatory to use a route reflector. Some people prefer not to, actually. The route reflector can be a customer or client, or it could be also a controller. They can coexist at the same time. They are very different functions. And what are the couple of examples here? I'm listing that all these products can be route reflectors, of course, including the virtual router. Now, important concept. There is just one direction in the process. Flowspec is unidirectional. That means we're going to instruct how packets should be handled from the controller to the customers, the client. But there is no feedback loop. There is no way to signal back through BGP. Yeah, I programmed the rule, and I'm matching this amount of traffic, and I'm doing that redirection or dropping this packet. There is no way you will be able to signal this through BGP. It's not bidirectional. For this, we will need to use other mechanisms. Could be show commands. Okay, that's great for your lab, but probably not in production. Or you can use netconf and using some XML models if you want to collect through your script what's happening on your router. So different means to do different things. You instruct how the packet should be dealt with, and you send back information through netconf. Also, everything is BGP-based. BGP Flowspec is nothing different than BGP. That means all the rules you know, all the principles, you know, about advertising information from hop to hop between iBGP and eBGP will be respected here. For instance, if you generate a rule here, through iBGP it will be sent to that client, but this guy having an external BGP session will also advertise the rule to this client on a autonomous system Y, and hop by hop it will go all the way. That's part of the principles. You will see that in reality, pretty much nobody is doing here. We have a couple of exceptions, but at the moment the norm is to have just internal BGP, and at best we have external BGP when we have a merger between two companies. But at the moment we don't have the rules being propagated over the internet. But the protocol allows to do it, just not, the reality is not, we see this not deployed like this. Now, let's jump into the protocol description and first answer the question, why do you want to use BGP? Why not some other technology like scripting, positioning the configuration remotely or with netconf or OpenFlow? BGP is very flexible. That's one of the big strengths of this technology. It's very easy to extend its capability, adding new AFI and SAFI. For example, we have been using BGP for many things, advertising labels, MAC address, v4, route unicast, multicast. Plenty of things can be done. And you can extend this capability just adding a new AFI and SAFI. That's what we are doing here. We're adding AFI and SAFI 1 and 133 to create Flowspec IPv4. OK. Second, it's by nature point to multi-point, or more precisely, point to point to multiple times point to point with a router reflector. It's also not limited to the boundaries of your autonomous system. It can exist all over the internet between multiple AS if you want to. And finally, BGP is controlled, mastered, understood quite well by pretty much everybody in this industry. You don't need to relearn a new technology. That's something, I suppose, at least on the service provider world, everybody understands and controls. Now, what we defined on the RFC 5575 is the following. On the matching side, on the description of the rule, we have 12 new NLRI, 12 types that will help you extract information from the field of your header, the layer 3 and layer 4, that means source and destination IP address, v4, in the case of this RFC, source and destination ports, ICMP type and code, TCP flags, packet length, DSCP fields, and fragment information. Based on all this, you will be able to identify specific traffic patterns and, let's say, flows. That's all what was defined in the initial RFC. Note, there is no IPv6, only v4. So what it's, if you take a look at the packet headers, that's what is seen in orange here. In orange, you have what the Flowspec can inspect. More important, what it does not inspect in red here. It's not possible with Flowspec in this RFC at least to match an MPLS label information or a MAC address. You're not able either to take a look at higher ISO layers. You cannot take a look at the URL in your HTTP request or DNS request. You don't inspect the content, or you will not match specific cookie. This is not NBAR. This is just limited to layer 3 and layer 4. Now, once we have a match, we will apply an action. And the action is signaled through the form of an extended community. We have 4 new types defined by the RFC, and we implement 3 of them. We implement the traffic rate, we implement the traffic marking, and the redirection. The one we are not supporting is the traffic action. So the remarking, rate limiting, and redirection to VRF is part of the RFC. Also, you can see there is no redirection to IP in the initial standard. A new RFC has been ratified later that helped clarifying the redirection to a VRF. Be careful, some people are confused by this one. It takes the form of an IP address, but in reality it's a route target. So it's only how to redirect to do VRF leaking, and that was the purpose of this RFC. But it's, I would say, most of the time is not capital to understand that. It's just for the vendors like us to make sure we are all interoperable. Now, all the rest all the other neat functions are coming under the form of drafts. So that's the following draft we support. Something to make the support of internal BGP Flowspec sessions, something to support the IPv6 address family, something to support the redirection to IP, which is very, very useful. Also, since it's BGP, we are benefiting from all the new other things, like the persistence, what we call LLGR. We will describe this in an example later on. The high availability functions, if you have redundancy between two active and standby RPs or RSPs. All this is working on BGP Flowspec too. Also, things like RPL filtering, max prefix, that's the kind of things you can program to avoid to protect your infrastructure, basically. Also, something which is not listed here, actually it is, but it's only valid for iOS XR. This draft is now supported on iOS XC platforms, ASR 1000, CSR 1000V. We support this very interesting function called interface set. So this one allows you to define which interface will program which rule. By default, on iOS XR, when you announce a route or rule, it will be programmed on all interfaces. With this one, with this draft, now we have the flexibility of being more precise. This rule will go on this interface. So if you have different roles, let's say core-facing, internet-facing, peer-facing, or different speeds, 10 gig, 40, 100, you may want to apply different type of rules. With this, you will have this flexibility. If you are interested to have this on iOS XR, please come back to me at the end of this session or send me a direct message on Twitter. We are very interested in your feedback. If there is a need for service providers or at least people running iOS XR, we want to know about this to prioritize the feature. All the rest of these drafts are currently not implemented, not supported. They are active work at IETF, and we'll see, depending on where it goes, whether or not we will implement them. It's always an open discussion. Quickly, which platforms support what? So it's a heavy chart, but if you want to summarize it quickly, I will say the first generation of the platform, CRS and ASR9K, does not support Flowspec. For instance, the CRS1 line cards, the 40 gig version of it, or the Trident line cards on 9K have not enough microcode space to support Flowspec on the data path. But every second generation and following, third and fourth, will support Flowspec. For the specific case of NCS 6K, now we are introducing on the roadmap for the second generation also. To note, XRv9K is implementing implementing the control plane. That means we have no data plane. If you want to play with data plane, you have to use this CSR 1000V. Still, with this list, you know that you see that you can play in your VirRole, in a virtual lab, with a controller, XRv 9000, and a client, CSR 1000V, and you can push traffic for that and see how it behaves. So you can already learn about it just in your virtual environment. What is not shown here is the NCS 5500. We postponed a bit the implementation, but now it's coming this summer on the second generation of LAN card. For instance, the one running with Jericho Plus and external TCAM will support Flowspec with the same list of features that we have on ASR 9K today. So we will have feature parity with 9K this summer in 651. Also, just for your reference, a list of the different types we support. So I will come back on the notion of fragment not being supported on some types. I will come back when I will list the limitations a bit later. Just for your reference, so we have 12 types for IPv4. We have 13 types for IPv6, but actually the 13th one is actually not implemented. So the IPv6 flow is not here. The big question will be, how far can we go? How many rules do we support? So today we are testing 3K, 3000 simple rules. By simple, I mean source, destination, address, and ports, plus one flag. That's what we have, and we can have 3,000 of them in a system. In reality, we can go much further. Some platforms, like the latest generation of 9K, I have customers who test 10 times more. and it was working fine. But at the moment, we are not testing it, so we are not officially supporting it. In Cisco, what we don't test is not officially supported. Doesn't mean it's a limit. Also, we have on the controller side, today, a software limitation to prevent to send more than 3,000. We will remove this limitation because now, of course, we realize that we will have to extend the number of rules on the hardware, so that's something we're going to remove. But I'm very interested, and if you have time after the session and you want to share with me what's your current needs, we talked in the Whisper room with different customers. Someone just told me 2 days ago that 25,000 could be a good number. Usually on the service provider world, 3,000 is considered as okay, but we are seeing more and more usages or use cases in the enterprise where people are doing traffic steering and they need much more rules than 3K. So I'm curious to get your feedback if you have time, if you have the will to share with me. I'm very interested in this information. Also, where can I apply my rules? So can I do this on every type of interface? Actually, not. You can only apply it on interfaces with layer 3 information. So you can have it on bundles, physical, VLANs, unbundled VLANs. But if you are trying to apply it on a pseudo-wire or an interface, a layer 2 interface, you will not be able to apply your rule. So it's only on layer 3 type of interfaces. And today, it's also only on ingress direction. Very important. You don't apply Flowspec on egress at the moment. Maybe we will change our mind in the future if there is a need. That still needs to be proven. Of course. The GRE tunnel today is not supported, no. Pseudo-wire headend, that's a good question. It's not supported as far as I know, but I need to double check. I don't think it is, but that needs to be double checked. Thank you. That's good questions. Where also another use cases, I mentioned that we are applying Flowspec on V4 and V6 interfaces, but sometimes you're going to have your traffic received with an MPLS label. That's a typical case I'm showing here, where we have a customer that is using 6PE to transport internet because they have an IPv6 free or MPLS only, if I want to turn it differently, core. The way it's working, they want to divert the traffic to a scrubbing center, and here we have only, you are received on a PE with the packets with an a 6P label. Nevertheless, we are capable of matching the IPv6 headers, ignoring the label. So that's something which is coming in a roadmap. It's not yet on this version, but that's going to come soon. And it's possible to inspect VPN v4, VPN v6, and 6P packets, just going to the upper layer, ignoring the label. Interesting feature we have is, as I mentioned before, every time you apply Flowspec, you apply it on all interfaces. So in my example, if I want to divert my traffic to router A, I will inject a Flowspec rule from my controller to this client. And what will happen is my traffic will be diverted and sent to the top. The problem is, in many cases, the packets can come back. Let's take an example. You are sending to a security appliance, and the good packets that have been identified as such will be re-injected. So a typical case of router and a stick. In that case, what happens is the following. You have a routing loop because packets are coming back on this interface, which is enabled for Flowspec. Packet will be matched to the destination. Yes, that matches this one. Then I will send it back, and you have a loop. Until the packets are exceeding the TTL, you have a routing loop. So we have a very easy way to overcome that problem. And actually, it's a key piece of, it's very important for many designs. We will disable Flowspec on the interface facing this router A. Packet will arrive here. It will match the Flowspec rule. It will be diverted to router A. Router A will re-inject the packet, but this time Flowspec is not enabled. It will simply do a lookup on the routing table and say, OK, packet needs to be sent on my right. I will show you that in a few minutes that it can simplify the designs in an incredible manner. Simplifying design means simplify troubleshooting, operation, and so on, not to mention the configuration. Just one word on iOS XC. The scale we have today, 256 or 250 on the virtual version, but that's what we can achieve. Important that we have the same feature on XC than XR, and actually we have more. As I mentioned, we have now interface set on XC and not yet on XR. But just for information, the scale we are reaching today. Okay, let's take a quick look at what is a use case, and we'll talk first about DDoS mitigation. So, few words, probably it's a stupid question. How many of you have been impacted by a DDoS attack already? No, that's okay, not everybody, that's good already. But yeah, quite a large number of you know, so I will not insult you, I will not spend too many time describing DDoS attack. Of course, it's a pandemic, we are seeing it for a long time, but it has been very strong with amplification attack in 2015 and 2016. Last year, everything was about Mirai and Satori botnets, IoT botnets. That means the amplification was not that trendy, but if you take a look at the recent Akamai or Arbor annual reports, you will see that amplification is still very, very present. We have attack at 600 gigi at top in some places. And they can only be done and achieved with amplification. So the principle, and the DDoS is a big word. People will have a different definition of what it is. Let's simplify stating that there is two big categories. I will call them the volumetric ones. That's the one we're going to talk about today. And the rest is application layer, something that can be handled by firewalls or application firewalls or detected by IDS, etc. So we're going to spend more time today on the amplification one. That's the one we want to identify and block as close as possible to the internet at the edge. So if it's coming here, it's already too late. If we are saturating the links for any reason, we lost. We can have the smartest DPI, firewall, whatever the tools inside. If you are dropping 80% of your traffic because you are trying to send more traffic than the interface can transmit, it's over already. So that's the most important thing. Also, the feature that you see sometimes in firewalls, anti-DDoS, are, we can discuss how effective they are. If you are really receiving 100 million new sessions per second, there is no firewall on earth that can handle that. So always a big debate and the way we should deal with it, but let's be clear, we want this addressed as close as possible to the internet. I will go over a couple of description of the different type of DDoS attack. They are sorted in three big categories: amplification, layer 3, layer 4, and stateful. That's maybe a gross simplification, but okay, that's as good as any other way to classify them. Just this one to illustrate what can be the victims. Enterprise elements in data centers, residential, also the SP service provider itself can be victims. So if you have targets in any of this, you can have a lot of collateral damages. For example, if someone is targeted an element of your data center, again, you can saturate potentially what is going through your interfaces. And everyone inside will be impacted. Likewise, if you have someone targeted a mail server or a DNS server on the enterprise, that will potentially saturate all the links and impact everyone else. More interesting, the most important attack category today is people on online gaming. People having arguments on Minecraft or PUBG or whatever, I don't know. They will they will buy what we call stressors or booters, and for a very small amount of money, they will be able to generate quite a lot of traffic that will potentially saturate the aggregation, or if not the aggregation, the first device like your CMTS, your DSLAM, if you are offering the residential services. If you start saturating this part, you will not only impact the victim, but everyone else on the area. That's always a story I like to tell. Is we have this customer in USA that has been, they're running a network for different universities and high school in the district. And one day they have a big outage, and they realize that the entire network was saturated because actually one server was under attack. It was a server used by some university, high school, to communicate, to share information with the parents, teachers and parents. And apparently some kids didn't want his parents to know something, like bad grades or something, and he paid for a stressor for a couple of days. And it was not only impacting this server, it was completely blocking an entire network. And these guys, they had at that time no money to invest on DDoS mitigation, and for them it was very, very bad. They had to ask help for upstream providers to be able to clean it. So that illustrates with a simple, maybe caricatural example, that the ratio, the difference between how much money it costs to generate an attack and what could be the impact is very disproportionate. Let's talk about what we can do with Flowspec. Flowspec can help you with this one, the amplification attacks. So let's, quick reminder, but I suppose it's obvious for everyone here, it's very easy to generate an amplification attack. You just need a couple of hosts. You need to forge the source address of your request with the address of the victim, and you will send it to high bandwidth servers on internet that will respond to this request, UDP-based, with a much larger answer. So you generate a small request, and the answer will be much larger. And the protocols that are vulnerable to this are the following. DNS, NTP, CARGAN, SNMP, SSDP can be used to generate amplification attacks. That one is shocking. RIP version 1. Remember before we have CIDR, before we have subnets on internet, 1990s, that was a protocol we used at that time. We have still plenty of devices and routers, home routers, that are running a RIP stack and can be used for amplification attacks. Port Mapper also was present. There is a couple of games like Quake or so on that can be used, Quake servers that can be used for amplification. Even if we are always talking about Mirai and Satori, like I just said, still the #1 attack vector in intensity are amplification. So you will see second is DNS, NTP, CARGAN, but the first one is UDP fragment. I will explain to you why they are #1 again today. So all this are still the most important attack vectors we have. Very cool site if you want, shadowserver.org. Yes, please?
Yeah, sorry to interrupt. I think there was a BCP 37, that basically asked service providers to make sure that they actually filter the...
Yes. So if I rephrase the question, we have I believe it's about 36, but yeah, we have a BCP, a best practice, that was stating that providers are supposed to filter the spoofed source. Indeed, if everyone was respecting that rule, it will solve the problem. But the problem for that is you need to implement functions like URPF strict, which are not always available. Let me give you an example. NCS 5500 does not support strict. It supports loose mode. And if you do that, also, it comes at the cost of some resources. So it's not very appealing for every service provider to use it. They should do it, but it comes at a cost. It costs you cycles, so the performance of your routers will be impacted if you are doing URPF strict. But I totally agree with you. If everyone was a good net citizen, that will be a problem. Some people will also argue that in some cases we have different paths and it's difficult to implement because not all traffic are coming on both directions through the same path, so it makes it a bit difficult to implement. But in essence, yes, you're right. So this site, every day, will scan the entire internet and will check how many hosts or how many IP addresses can be used to generate amplification attacks. So if you go to the website, you go on the left columns, you will see all the protocols I listed before, NTP, CARGAN, etc., NTP monlist, SSDP, and you will see that what is really scary is the number is not decreasing. If you take a window of 1 year or 2 years, this is almost flat. It was big at the beginning, then now it's reached. That means we are no more fixing or patching these servers. That means it's going to be here forever. You will still have amplification DDoS attack for the rest of your life. Deal with that. You have to accept that. Until we move to something smarter, but it's not something that is about to come soon. So the number here is very concerning. The number of SNMP servers that can be used is almost 4 million. The number of monlist NTP server answering to monlist request is flat to 40K. So that means, okay, amplification, it's here, and will be here for a long, long time. The good news is amplification are very easy to tackle. Because of the nature of the packets, you know very easily how to identify them, simply because they are way too big. So an example here, I have an NTP packet that I don't remember the exact size, but let's say if I have to make up a number, the payload should be 400 bytes long. The one you're going to see on amplification cases will be much larger. They will have 1,500 byte long packets. So we can easily, with Flowspec, create a rule to say, okay, from the controller, every packet targeted to the victim, 2111, with port UDP 123, and packet larger than, let's say, 1,000 bytes, should be dropped. And we will apply this on the incoming interface. And we will be able to apply that rule at line rate. So if you have an 8-port 100, you can do that at 800 gigi. You don't need to send your packet to your expensive and precious security appliance. You want to do that since it's basic and simple on where's the horsepower here on your routers. So that's a good practice here. Flowspec should be applied on all the amplification attacks directly here. And you can use that for everything, your NTP, your DNS amplification, your SSDP, etc., etc. Also, I mentioned before that the number one category of attack is the frag. Why so? It's simply because when you generate or you trigger an amplification attack, it's very common that all the way, sometimes at the very first interface, but sometimes also on the path, you will have an MTU which is smaller than the packet size. So it will break the packet, and you will have fragment. The fragment has no indication what was the initial protocol. You just have a fragment, and you need to use the fragment information to recreate the packet. So that's why in my list, the number one vector was frag. They are all coming from different type of amplification, actually. And we are able, with the same Flowspec rule, to match that the fragment field is set, and we want to drop this if the packets are targeted to this victim. So fragment, amplification, all handled by Flowspec. Now, what about other type of attacks? ICMP flood is also very common. I do have 09, I believe, is very often seen. You will see a lot of ICMP requests coming from the internet targeted to your victim. And that's something we can also address with a simple Flowspec rule. Destination 2111, ICMP type 0, code 9, we drop. Again, when we apply that rule, that means none of the other traffic targeted to 2111 is impacted. Only this very specific. So you're doing surgery. You are doing very fine detection of the packet, and you drop only what is matching this exact rule. So and you do that at line rate on the router. Last will be the stateful attack. When I do receive a TCP SYN flood, or I do receive an attack on HTTP like Loic, can I do something with Flowspec? First of all, first answer, can I address it on the router? The answer is no. Flowspec is not smart enough to figure out which packet TCP SYN is good or is bad. You need something intelligent, smart enough to challenge the session. If you receive a TCP SYN, you need to send a SYN hack with a different sequence number to make sure the hack you receive is good. So you need some level of smartness. Not crazy smart, but still smarter than what Flowspec can do. Flowspec just inspects in one direction what are the fields. But still, Flowspec can help you here, in the sense that it can be used to divert this specific traffic to your appliance. That's what I'm doing here. I will just divert the port TCP-AT targeted to my victim to this. That means I will not divert the rest of the traffic targeted to 2111. I will send less traffic to my appliance. That means I will be able to use more of the cycles, or more of the CPU cycles here, to do more DDoS mitigation on my appliance. So Flowspec is useful. It's not fixing the problem, but it improves, it optimizes the usage of your resources. All this can be, by the way, can be automated. Since the version they released 2 weeks ago, Arbor is capable of doing DDoS mitigation, automated mitigation with Flowspec. They were able to do manual in the past. They were able to do diversion also. Now they are completely automated the process. I have customers that are using full automatic automation for all the subscribers. If they receive a big attack to one DSL customer, instantly they will drop it with automation. So for some key assets, maybe you don't want to do that. For residential, that's definitely something you should use. Now, let's take an example how Flowspec can be used to improve a design. So the demo here is actually something I will not show. It's on. I'm just illustrating that we can use in a quick demo how to divert the traffic to the appliance for TCP/AT, and we can also how we can drop a UDP 123 NTP attack at the same time. So I invite you to go to this website. That's something you can watch offline to see exactly what are the steps in the GUI using the Arbor SP. But it's just an example. Also, something very cool we have on the SR9K when we're running with the VSM is called the dynamic blacklist offload. So that is an interesting feature in that sense that you will take the smart capabilities of the VSM running the Arbor app software. When we will divert a packet, when the packet is received and we prove that the source is legit, but the host is corrupted, it's like a botnet member, then we will program a rule to the router automatically with Flowspec to say, hey, everything coming from this guy, for 1 minute, you drop it. So all the traffic received will be dropped and not sent to this appliance. So that means this appliance can be used for something else in the meantime. After 1 minute, we're going to remove the rule, and then the traffic will come back here. And again, if the packet is received and it fails to check, we prove that it's corrupted, then it will re-inject the rule for 5 minutes, and the process will repeat. So you are kind of offloading, because you know that statistically speaking, everything coming from this guy is bad, it's part of a botnet, I'm going to drop it. And that's a very fully automated process. So that's easy, a good way to automate and use Flowspec in different ways. That's something for you to think about. What are the benefits of doing a rate limiter to a certain amount compared to 0? I have always this discussion with customers. They say, oh, I'm going to rate limit this attack to 100 meg. OK, if you do that, why don't you drop it completely? Because if you do 100 meg, that means you're going to drop a lot of good packets the good ones that will pass through your small amount of traffic will be received by the victim, but they will miss a lot of things, and they have to request a lot of TCP resend to reconstruct the flow. So it will occupy a lot of resource for nothing. The service is impacted. Also, I will show you that in a few minutes that we have, when we apply a rate limiter, it's actually applied on the NPU level. So if you apply, let's say, 100 meg, if you have 2 interfaces, that means 50 each. If you have 1 interface, it's 100 for this interface. That's interesting because if you apply 0 and you divide by the number of interfaces, that would be 0. If you apply 100 and you divide by 6 or 2, of course it will not be the same. That's an argument against using a number instead of 0. Again, I'm open to counter-arguments if you have any. I'm interested to get your point on that. So Flowspec, I just explained, that's very useful for amplification. That's just not magic. That's also something people are always expect, OK, I'm going to install Flowspec and DDoS is fixed. Not really, because all the attack you have from IoT networks that are legit requests, there is no way Flowspec can help with that. So it can optimize just sending what you want to your smart device, but if you have no smart device, there is no magic here. Flowspec is meant mostly for amplification. OK, let's take an example of a model, something that is a real life. I just changed the topology, but it's something we really seen in a production. It was a European network, spread between different countries. And it will illustrate how it can be optimized some existing architecture with Flowspec. But again, it's not meant to be a best practice. There is no best practice in the matter. Every time we talk to customers, we have to go on a whiteboard, figure out what type of technologies they use, what are the potential limitations, and how Flowspec can be used to improve that. But there is no best practice. I'm just showing one use case. Okay? This is what they were doing before they introduced Flowspec. We have 2 routers here, the router J on the top, the router M on the left. They are all positioned in different POP. And here we have a security appliance connected to the box. Here we have a VSM card on a 9K. And they define what they call a dummy route. Dummy route is 10.51.51.51. It's pointing to the local security appliance. But no traffic by default is going through 10.51.51.51. So that means this route, by default, does not transport any traffic. But they define it on every single port. OK. Now, when they are under attack, when they identify using NetFlow that there is an attack to the victim 2111, they will inject a BGP route with the next stop 10.51.51.51. What happened is the following. We create a recursion. So we create this entry, BGP, pointing itself to the static route. And that way, the traffic now targeted initially to the victim 2111 is diverted locally. So now it goes to my VSM card here, and here it will go to my appliance. OK, that's cool. I diverted my traffic. Now I'm able to do some magic to figure out what packets are good and which ones are bad, and I need to reinject the good ones. So the problem to do so is I'm creating a routing loop. If I'm just reinjecting the traffic without doing anything, the packet I receive with destination 2111, it goes through my recursion chain here, and again, it's sent to the guy. Now you get it. I will use Flowspec with the capability of disabling interface. That will be one of the tricks. Also, the problem we have is when, before that, we try to find a way, and the only way we had at that time is to create multiple parallel paths to each exit point, basically using two sub-interfaces on the same interface, and defining what we call clean VRF. This VRF in blue is called clean. When the packets are received from this, that means they are good, they are clean. They are going here, and now we have an exit point to K or L. That means we also need to learn IGP, because potentially, if we send it here, but the best route was this, I have another routing loop. So I need to make sure that the best path I will use, or I'm able to do load balancing. So that, in terms of traffic, I was able to do my load balancing here and here. So if I summarize how to do this before BGP Flowspec, you have to define a dummy route everywhere. You have to define VRF, clean VRF. You have to define multiple paths, assign one of the paths to the VRF, and you have to learn IGP in both the global routing table and your VRF. When it's troubleshooting time at 2 in the morning, that's not great. It's kind of a complex topology. What we propose with Flowspec is the following. Oops, sorry. We have no more dummy routes. Now we will be able to inject through direct BGP peering the Flowspec rule that we want, stating that for 2111 and only for port TCP/80, that's more granular than what we used to do before with my BGP route, I will divert it to the next stop of my appliance. So I'm sending less traffic. There is already one improvement here, and I just divert it here. Same story on the other pop with the router J. And I will disable my Flowspec on this interface 000.2. That way, when the packets are coming back, I will just do a normal lookup in my IGP to figure out where the packet should be sent. In that case, here it's easy, that's router I, but if I have 2 exit points, that's much easier. I will find the best way, that would be K, or I will do load balancing if they are equal path. That's very useful. No more VRF, no more dummy routes, no more parallel paths, just simple Flowspec injection and disabling Flowspec here. So it simplifies the design greatly. That's just an example, but that's something you can use in many other cases. Let's take a look at other cases. I have a customer that wanted to do in an IP only, no MPLS here, just pure IP. They wanted to do unequal cost load balancing. Actually, that means they have an exit point here, which is a NAT, a translation address tool, to get out to internet at 80 gigi, and they have a second exit point at 20 gigi. And if you want to do with just normal routing, unequal load balancing to 20 and 80, it's very complex to do. You have to play with a lot of static fake routes. That's possible, but it's a nightmare to manage. With Flowspec, they had the following idea. They identify what was the amount of traffic blocks of users were generating. That means this guy at peak hour, it was 10 gigi. This group, 10 gigi. This group, 30 gigi. That way, they're able to inject different Flowspec rules, and they will match the source address. If packets are coming from this source, I will send them here, and hop by hop, every router will pass it to the exit, to the point of exit, which is here. So if I take every flow one by one, I will have first flow representing 30 gigi will go to the top. Second group of flows will be 10 gigi to the bottom, and that last one will also go to the top. So I have total 40 and just 10 here. I do something which was virtually impossible before this technology. Of course, another option will be to move to everything to MPLS and do RSVP-TE and stuff. Again, quite complex compared to this approach. Another use case here is how to use Flowspec to categorize with a different QoS quality the different flows. I'm showing here a communication inside the network between two data centers. I have database synchronization, very important business critical operation. And unfortunately, the path to my scrubbing center, the place I have all my security device, is the same that the one used by my backup. And if I have no congestion, that's fine, but if suddenly I have more DDoS traffic, I'm impacting this. So the easy way to fix that was to use Flowspec to, of course, redirect to the VRF dirty that will lead the packets to the scrubbing center, but on top of that, position a DSCP field that will be mapped as an EXP MPLS field in a core that is less important than the default IP between my data centers. That way I give less importance, less precedence to my DDoS traffic, and I will not impact my service. So Flowspec here to redirect to a VRF plus to mark a DSCP to say it's important, it's not important. Another example again, that's a transit provider offering internet connectivity to other autonomous systems. They have a commit to 10 gigi, and they are under attack. Let's say they have a 50 or 100 gig attack. So all the traffic is transported over my transit provider and dropped here at 10. What is often seen, I will not give names, but it's a common practice, is to position a Flowspec rule when they detect the customer is under attack, and they will start now dropping traffic at 10 gigi at the value of the commit here. For this guy, it's the same, because packets are dropped. We try to send 50 to 10, so we drop 40. But the difference is for the transit providers, they are not filling up the pipe on the way. Good or not, it's not for me to say, but from the customers, there is no difference. Even better would have been, of course, to give the capability to this customer to advertise with Flowspec that I want to drop the traffic. That would be an ideal world, but it's not always working like this. Now, what can be done for the enterprise? I'm just giving you a very simple example here. Enterprise, it's seen very often in the financial, insurance, retail, utilities, and so on. We have different paths with different security appliance. And we are using Flowspec when the packet is coming from bottom to top to classify the traffic. Let's say you have your SAP or your business intelligent type of traffic going. It will be matched and sent to a specific path where it will be analyzed by WAF or specific firewalls. You have your mail, it will be sent to your specific path where you have your anti-spam, different type of cache for HTTP and so on. So they differentiate the traffic based on the protocols, and they send it to different paths, and they do it with Flowspec. In the other way, when the traffic is coming from the top to the bottom, and they have remote offices, they will use the same, also Flowspec, to differentiate the path of the traffic. Important business traffic will use MPLS network. They pay expensive price for this transport. Less important traffic will use IPsec over internet. So that's typically SD1. They're just doing it the same way. And we see this design in many, many places. When you apply this, obviously you need much more rule than the 3,000 we define. If you want to be super granular, you will need dozens of 10,000 of rules to be able to do all this classification. But that's very interesting. No more DDoS mitigation whatsoever, just traffic steering. Also, I was talking with my colleague Jose recently, and he's working on a project where they will use Flowspec to divert the traffic to different segment routing policies. With policy, we used to call them tunnels in the past. Now we say policy, but they are in a sense, just the same thing, stack of labels. And depending on the path you want to take, path with lower cost or optimized latency affairs, you will use Flowspec to steer the traffic inside these tunnels. So Flowspec now does not do any kind of DDoS affairs anymore. It's only about steering and pushing the traffic in the right direction. OK, let's talk about the configuration. I still have half an hour, and it's good enough because it's very simple. Flowspec is configured between a client and a controller. First of all, defining an adjacency. So you will define your neighborship relationship, I will say. And you will just use a specific address family for that. Then on a client, you will have to define which interface should be configured. On the controller, you will advertise the rules. And we'll see that the rules are following the same configuration principle that we have on, let's say, QoS, modular QoS CLI, MQC, when you define a class map, a policy map, and you apply it somewhere. That's exactly the same principle we're going to use for the description of the traffic and the actions. So it looks like this. On the client and the controller, we will share the same first part of the configuration. We define a neighbor using the same address family IPv4 Flowspec, the source from the lookback, and the same router autonomous system, which is 1. And I call this neighbor group with my neighbor, and I establish a BGP neighbor relationship between the two. On the controller, I will define a specific Flowspec address family service policy. I will see that in a second. On the client, I will just say, by default, you install it on all interface. That's where we will also be able to say, this interface is disabled for Flowspec. That's at that level, we'll do that. On the controller side, we have now the policies that will be used to define the rule. First, the class map, that's the description, multiple match elements in it. Then we have the policy map that is calling the class map we defined, and we apply the action, for instance, rate limit or redirect. And finally, we configure all this here, so it advertises to the client the policy we defined. It's very simple. So let's see, that's just for reference, to explain that if you define multiple policies and you call them, or if you define one policy with different class map, it's the same. Eventually, on the hardware, it will take the same amount of space, just for your reference. Another example, if you are curious to see how it works, there is a video on YouTube to explain the different principles. I define, or I explain in extensive details in the backup section how it can be used if you want to troubleshoot, to monitor the amount of resource you have. If you want to understand how it works, it's on the backup slides. I will let you take a look at that. One simple example, and I'm just taking one. All the rest are present on the backup section, is I want to advertise this, match destination IPv4 with this address. It will be actually translated in NLRI. That will be 0x01, because that's a type 1. A match destination is type 1. Then I will have in 18 here represent my /24. And finally, in red, 51 FDC1 represent my prefix. That's what is actually exchanged between the two BGP routers. On the other side, it will receive this, and it will be able to transform it into, or translate it into something that will be programmed on the hardware. That was a basic one. In reality, you can configure much more complex rules. If you see what is the NLRI, that's not something you can do manually, but for routers, not a problem. What it does is the following. You have multiple match statements. If you have multiple match, that you have to use a match all. It's a logical AND. AND. That means you need to match and to respect every single statement to be a positive match. But inside each match, you can have multiple values. And here, it's a logical OR. Yeah, that means the source port can be 10 or 20 or anything between 30 and 40 and so on. So if you do that, you can have up to 5 elements on your match, and you can use ranges. So that's this logical AND between the matches and logical OR inside each match statement. And that's what will be actually seen and translated on the client side and programmed on the hardware. Now, what about the action? The action is, I take an example here with a police rate. The action is transported on the form of an extended community. And for the particular example of the police rate, it's actually expressed in byte per second. So you're going to have to multiply by 8 if you want to see how much megabit per second it actually represents. But same logic, that's something you're going to define on your policy map. First, you need to call the class map you have before, that's the first rule you have, and then you apply the action. So I'm showing here how it's behaving. This is a graphic coming from, again, Arbor tool, but that's just an action of dropping all the packets. I will see that all the packets I matched are being dropped. OK, very easy. Now, the second option is how I can be able to do the redirection. In the RFC 5575, the very first RFC, it was only about redirecting to a VRF. So when I do receive my packet in my global routing table, I'm able to do some leaking into a VRF blue, and then I will do a lookup in the table present on this VRF to figure out where is my destination, my route 1232/30. So it should be a .4 actually. So this is what was defined first. Second, we introduced something a bit simpler, is to be able to advertise a new next stop. We don't use the IGP or BGP table. We will use this information to redirect like I've been showing before. So this can be configured like this. In a class, you do a redirect next stop, and that's what will be advertised on the other side. Again, I'm just going through a couple of examples. They are, I believe, fairly simple. There is no rocket science here. This is for more for your reference. Actually, the next stop information is a bit specific. So it's not transported as an extended community, but as a BGP attribute. I would say that's just technicalities, just for your reference. That's more interesting. If you start playing in your lab, you will define on your controller your rule. But you need to make sure the next stop you are defining is present on the table of your controller. Let me show you why. I have no route to my next stop, this address. And if I take a look at the client side, I see that I received 0 prefix. It's a simple BGP principle. If you have no next stop, you don't advertise it. That's why it's recommended to use a fake fake static route for this particular next stop. If it's present, it could be pointing to null 0. It can be pointing to a real interface, not important. Now you will be able to advertise your rule to the client. Now the question will be, do I need to have the next stop on the client? Ideally, yes, but it's not that important. Let's take an example. I'm trying to redirect my traffic from on my client to a specific interface, but this interface went down. It's shut down. My route disappeared. So my next stop is no longer present on my client. Even if my controller advertises this, it will be seen as inaccessible and not programmed by Flowspec. That's very important. We don't want to drop all the packets because the next stop is not reachable. So now, since the next stop is not here for any reason, it will simply use your OSPF route or your BGP route to send the packet to the next hop. So you're not creating black hole with this. It's important. It's possible, I show you, it was possible to mix different match statements on the description, but it's also possible to mix multiple actions. We can have rate limit and DSCP marking and redirect, but they will be applied in that specific order. So we can do, again, a rate limit to 10 meg. I will mark to EF, and I will redirect to this particular next stop. That's possible, and we can do that. As you can see here in the action, you have multiple actions present here. What is not possible is to redirect to a VRF and force the next stop. When the packets are going from global routing table to VRF blue, in my former example, then the next stop needs to be reachable on the table for this. You cannot say, oh, I'm going to force you to go to this next stop. That is not supported by the standard. So that's important. Also, you cannot do hop by hop. So you cannot do source-based routing or policy-based routing like this, hop by hop. Just one single next stop, and then that's over. Very, very, very useful feature, what we call the LLGR, long-live graceful restart. It's not specific to Flowspec, but it's for every BGP function. when you establish your BGP address or neighboring, you will negotiate a timer. For instance, we take 6 minutes, and we say, if anything goes wrong on this BGP session, I will maintain my Flowspec rules program in hardware. So let's say I lose my session here, because let's imagine I'm reloading this guy for maintenance upgrade. I will still have my rules present for 6 minutes. I see it started at 3:50. Now I have already 40 seconds elapsed. And when I will reach the end of this timer, I will expire this timer. Finally, I will remove my Flowspec rules from hardware. So that helps if there's multiple situations where you have your controller under attack and it's no more responsive, or if you're reloading, or if you have outage, your rules are not suddenly disappearing. Some other people will prefer to have multiple controllers. Okay, that's a good practice too. If you have rule A, B, C, D here and rule B, D here, they're going to be received and programmed on the client. But there is no mechanism defined by any standard to synchronize the rules. You have to make sure that the rules you program on controller 1 and controller 2 are similar. If they are not, that's not the protocol to figure out that there's something wrong. Also, if you're advertising contradictory rules from here to here, or even 2 rules on the same controller that are giving different instruction, the standard is taking care of this. So they defined a tie-break to make sure which rule will take precedence over the other. It starts from the order of the NRI types, but if there is no differentiation possible, let's imagine you have the same source IP destination, same source port destination, so you are going to all this level, type 6. Now it will inspect the content, and it will compare the address that you defined. It will start with the more specific address. If you have a /32, it will be better than a /24. And if there is even no way to differentiate them, it will perform hashing using the memconf function in ISO C standard. So everything is handled by the standard, and if the implementation is correctly done, it will not depend on vendors. You can have vendor X and Cisco, it will work perfectly, everything should be aligned. I'm taking just an example here to show that if I have multiple rules, one is advertising to a next stop, and its point actually matching the destination with a /32. The second is pointing to a different next stop, but a larger prefix length, /24. You can see that only the more specific is actually transmitting traffic. So that's something well defined and perfectly handled. Also, an interesting one is what we call the safety net. It's very important if you start opening the capability to your customers to program, to inject your Flowspec rule, that they are only able to do it on their own block. We don't want a customer A to be able to influence traffic on customer B, or even worse, your own traffic, and start messing with your BGP or something even worse. So that's a very nice way of filtering. It can be done in different ways. You can permit everything or accept this, or you can deny everything and permit. You can take it in different angles. The example I'm showing here, we are authorizing this particular prefix set, 1110/24 up to /32, and we're injecting 2 different rules, and we can see that only the first one, which is actually part of this block, is accepted. Just simple illustration of what I've just explained. Simple way to control what's going on. Important, we are not matching the action here, only matching the source and destination. We're going to see in the limitation list that it's a big missing piece. I will come back to that. Also, we have a consistency check. In the past, it was possible to define whatever nonsensical rule you want. It was possible to say, I want UDP traffic with ICMP type 7. Makes no sense, but the controller will send it. Now the controller is a bit smart, and he will do some verification. Okay, you cannot do a port without UDP TCP. You cannot position a flag on UDP. Or these kind of things are now tested to make sure that what you advertise makes some sense. I mentioned that before. I'm going to repeat it. The way you're going to control or monitor everything will be through CLI, okay, not very scalable, or through netconf. No SNMP MIB. There is no SNMP MIB at the moment. Also, there is still a discussion at IETF to get young models. At the moment, they are all proprietary. So this is documented, but still, it's not a standard. It's not SNMP to get to extract information of your counters. Some very interesting aspect is what happens when I have Flowspec, but at the same time I have other features configured on my interface. Simple example, I mentioned before NetFlow. You are under a DDoS attack. Your NetFlow sampler will generate records. I mean, yeah, it will generate records to give you visibility. That's how you're going to know you are under attack. When you inject your Flowspec rule, it's very important that you are not suddenly completely in the dark. You want to know if the attack is still ongoing or stopped. So that way you can decide whether or not you want to remove your Flowspec rule. This is before I apply my Flowspec rule on the router. I see that for this particular stream, I have an output interface and a status, a forward status being forward. Once I apply my Flowspec rule, I start dropping all my packets. And that was actually, I don't see it here, but yeah, I see that my output interface becomes 0, it means it is dropped, and the forwarding status becomes drop ACL deny. So that's great because from your management perspective, your monitoring perspective, you will still have visibility that something is going on. When you will see that you have no more flows on this, that implies the attack is no longer present. You can decide to remove your Flowspec mitigation certain thing. Another one is if I do have access list and to protect my infrastructure, and I want to apply a Flowspec rule which is contradictory. An example is I'm advertising a rule to divert my traffic to this address, but at the same time, the same traffic matching this thing is supposed to be dropped. And what we see is I generate my traffic and I see a lot of matches on my access list and 0 packet being matched by Flowspec. That's a good news. That means your access lists are more important and they're going to take precedence over a Flowspec. So someone messing up a configuration on Flowspec will not suddenly open the door and create security holes. Access lists take precedence over Flowspec. Another example is access list-based forwarding. So that's one, is when you have what we call also PBR, policy-based routing, you make a decision no longer on the destination address, but some other parameters. This one here is diverted. I have 3 options, and I use a PBR from right to left to send it to this interface, the .2. Once I advertise my Flowspec rule, I will see that my traffic now goes there. That implies Flowspec takes precedence over ABF. And the reason is simple. They are using the same data path, the same forwarding mechanism in the router. So to summarize, NetFlow still works with Flowspec. Is still sampling before the Flowspec is dropping the packet. Second is access list takes precedence over Flowspec. Last is Flowspec takes precedence over ABF. Now let's move to the last and very important section is the limitations. I insist on this aspect one more time. This is a dead horse I've been on too long, but if you are already saturating your upstream links, there is no magic here. You cannot do anything. If you are dropping vast majority of your packets upstream, there is no way you can magically recreate the packet that disappeared. That's obvious, but I have to repeat it. There is also today no capability to do match any. So that's an interesting one. If I do have multiple match statements, for example, I wanted to have multiple match entries of match this address, this address, this address, I cannot do a match any. I need to do a match all. It's a limitation due to the way we implement the class map, service map, and so on. And today, there is one example called the type 4, where we are supposed to match both source and destination at the same time. It should be the same. If you do that, it's the same value. And it's not supported. It will, when you try to commit this configuration, it will tell you, no, I only support match all. And the only way to overcome that limitation is to configure 2 rules. One to match this source, the other one, second one to match the destination. Okay, that's not dramatic, but that's something to know. Also, something I mentioned before. If you are applying a rate limiter, that means you are in total disagreement with my former point of recommending that we drop everything instead of applying a rate limiter. Keep in mind that the rate limiter is per NPU, per forwarding ASIC. If you have one interface connected to your forwarding ASIC, and you define a rate limiter of 25 megabit per second, that's what will be the rate limiter. That's what you see here on this Ixia snapshot. But if you have multiple interfaces, you're going to have to divide that, because that will be not at the interface level, but one step up at an NPU, that you will have your rate limiter. For instance, you see 25, 25 here. One more time, if you do 0 BPS, you don't care how many interfaces. That's one more in my argument that you should not do that. Another thing of interest, if you are trying to match fragments, and we are not supporting the down fragment and the last fragment flag. We are supporting is and first on CRS and only is fragmented on 9K. Still very useful to match the amplification attacks that are coming on two flavors, fragment and protocol like NTP and so on. But that's something to know that depending on the platform you try to apply it, sometimes it will not be supported. You don't support either lists and ranges for ICMP. That's if you try to do ICMP type 0 and code 1 to 9, it will not work. You will have to define one rule for each type. So sometimes it can be a bit long. But that's the only workaround we have. You have to configure multiple rules today. That's also something I mentioned. We have this very cool feature to filter the rules to make sure they are coming from the people that are allowed to send them, but it's only limited to the source and destination address. We are not filtering today the action. That is kind of problematic, because if you customer decide not longer to only drop the packet, but they say, oh, my packet, I want to remark them with EF, expedite forwarding, or I want to redirect them to a next stop, there is no way to limit that. So I understand it's annoying, but if you consider the way we are offering this to the way we design the Flowspec network, most of the time they will have access to the last router before connecting to their network. And in that case, if they remark the traffic to EF, that only impacts their traffic, or if they do a redirection, it goes nowhere. But still, it's something we need to improve. I believe that's going to come in next releases. We will do efforts to be able to filter the action to limit only drop, authorize only drop. Also, I mentioned that before, and I'm going to repeat it one more time. If you are interested in having the capability of applying the Flowspec rules with the level of granularity of deciding that rule goes in this specific interface, it's only coming with this particular draft called interface set. It's supported today on iOS XE, ASR 1000, and CSR 1000V. It's not supported on any of iOS XR, so ASR 9K, CRS, and CS, etc. If you're interested, get back to me. I will need your feedback. That's very important for that. Also, now that leads me to the conclusion. And it's going to be very quick. One more time, Flowspec is nothing magic. It's just a tool that can be used for multiple purposes, depending what you want to do. DDoS mitigation, particularly for amplification attacks, but not able to do much with stateful attacks, aside redirecting them. So that's still an improvement. Also, it's used more and more as a way to redirect the traffic, what we call traffic steering or traffic engineering. And we are seeing more and more use cases. So what I've been showing you are cases coming from customers. I'm sure there is much more, and I'm actually very curious to know if anyone has any innovative ideas that we didn't even think about. Just a tool so people can do wonders with different new tools. If you want to start playing with it, you don't even need real routers. You can use Viral, and you can use the XRV 9000 as a controller, and you can use the CSR 1000V as a client, and you can start learning, building scripts, doing whatever you want. So you can build your own playground virtually on your laptop. So that's it for me today. If you have any question, one more time, don't forget to use this tool and to rate that session. I thank you a lot for your time And that's all I have for you guys. Thank you very much.